I'm Dr. Jason Brinkley, and this is mass-based concentrations. By the end of this video, we will be able to calculate solution concentration in mass to volume percent, mass to mass percent, parts per thousand, and parts per million. Determine the quantity of a solute or solution from the concentration of a solution. So concentration is the mathematical expression of the amount of solute in an amount of solution. This could be in many different forms, and in fact, there are literally many different ways that we can express concentration. The ones that we're going to focus on in this video are mass-based ones. So mass to volume percent, mass to mass percent, PPT or parts per thousand, and ppm or parts per million. So the mass to volume percentage is simply the grams of solute over milliliters of solution times 100%. So let's do a problem. Calculate the mass to volume percent of a 0.060 liter solution containing 10.0 grams of NaCl. So the mass to volume percent is the mass of the solute in grams over the milliliters, the volume of the solution in milliliters times 1,000, or sorry, times 100. I'm getting a little ahead of myself here. So we've got the mass of our solute as 10.0 grams of NaCl, and the volume of our solution, SOL apostrophe N is solution, the volume of solution is 0.0600 liters. We need to convert that to milliliters first, so this is going to be 1,000 milliliters is 1 liter. So this is actually 60.0 milliliters. So now, let's plug this in. 10.0 grams of NaCl over 60.0 milliliters times 100 is going to equal 0.167%. Sorry, not, well, I forgot to multiply by 100. 16.7%. Let's do another one. 50 grams of argon gas are diluted with 80 grams of helium gas in a 476-liter container at standard temperature and pressure. Calculate the percent mass to volume of the argon gas. Now this problem looks really complex at first, but it's actually very simple. The 50 grams of argon gas is our mass. The 80 grams of helium gas we don't care about. Why don't we care about the 80 grams of helium gas? Because it's not argon gas. It's not the solute that we're worried about. Okay? In fact, it's the solvent, and we're not going to worry about that because what we're looking at is the volume in the 476-liter container. So our volume is 476 liters. Now remember that we've got to turn this into milliliters. So 1 liter is 1,000 milliliters. And our percent mass to volume is equal to 50.0 grams of argon over 476,000 milliliters times 100 to make it a percentage. And this becomes 50 divided by 476,000 times 100 is 1.0 5 times 10 to the minus 2% argon. Let's do one more. Calculate the mass in grams of sodium hydroxide required to make 2 liters of a 1.00% mass to volume solution. So, remembering that percent mass to volume is equal to the mass of the solute over the volume of the solution in milliliters times 100. We can rearrange this equation if we know the mass to volume percentage and we know the volume of the solution. We can calculate moles of solute. So what I'm going to do is first I'm going to take my percent mass to volume and divide it by 100. That gets rid of my percentage portion. Then I'm going to multiply by the volume of the solution in milliliters. That's going to give me the mass of the solute in grams. So now I can just plug in my numbers. My percent mass to volume was 1.0%. So 1.00 over 100 times my volume of solution in milliliters. This is at 2 liters, so 2.00 liters times 1 liter, 1,000 milliliters is 1 liter. That means this is 2,000 milliliters. Gives us 20.0 grams of NaOH required. Mass to mass percentages are another way that we can express solution concentrations. This is the mass of the solute, grams of solute, over the mass of the solution in grams times 100. So let's do a problem. Calculate the mass to mass percent of oxygen gas in a mixture containing 20 grams of oxygen gas and 80 grams of nitrogen gas. So now we've got the mass of our solute is 20.0 grams of O2. What is the mass of our solution? Well, we can't do this in a volume percentage because volumes are not additive, but masses are additive. So the mass of the solution is the mass of the solute plus the mass of the solvent. In this case, 80 grams of nitrogen. So this is 20.0 grams of O2 plus 80.0 grams of N2 equals 100.0 total grams of solution. So now, percent mass to mass is equal to 20.0 grams of O2 over 100.0 grams of solution times 100 to make it a percent, and that is 20.0% O2. Let's do another practice problem. Calculate the composition of each of the following solutions in mass to mass percentages. 21 grams of sodium chloride in 100 grams of solution. So for part A, mass of the solute is equal to 21.0 grams NaCl. Mass of the solution is equal to 1.00 times 10 to the second grams. percent mass to mass is equal to 21.0 grams of NaCl over 1.00 times 10 to the second grams times 100, or 21.0% NaCl. Now for part B, this is a little bit different. 21 grams of sodium chloride in 5.00 times 10 to the second milliliters of solution. And we're also given a density. So the first thing we need to do is we need to write down mass of the solute, which is 21.0 grams of NaCl. But we've got a volume of solution equaling 5.00 times 10 to the second milliliters. Now we could do a mass to volume percent quite easily because we're given mass and volume, but we're wanting a mass to mass percent. So now we need to use density. Remember, density is equal to mass over volume, or mass is equal to density times volume. This will allow us to get the mass of the solution. So this is equal to the density, 1.12 grams per milliliter times 5.00 times 10 to the second milliliters. And that gives us 560 grams of solution. So now I'm going to change colors so that we can follow through here. Percent mass to mass is equal to the 21.0 grams of NaCl over now the 560 grams of solution. That should be 560 with a decimal point. Times 100. So 21.0 divided by 560 times 100 is 3.75% sodium chloride by mass. We really should have the unit mass to mass percent, or percent mass to mass, so that we know it's a mass percent, not a volume percent. Finally, we have parts per thousand and parts per million. Now, parts per thousand and parts per million are often used to express concentrations that are very, very small. They don't have to be, but that's usually how they're done. Basically, it's the same sort of concept as doing a percentage by mass, except instead of multiplying by 100 for a percent, you multiply by 1,000 for parts per thousand and by 1,000,000 for parts per million. So let's calculate the ppt and ppm of oxygen gas in a mixture containing 20.0 grams of oxygen and 80.0 grams of nitrogen. So ppt first, we know that the mass of our solute is 20.0 grams of O2, and that the mass of our solution is equal to 100.0 grams of solution. We did this problem before, okay? But instead of a percentage, we're going to get the thousands. So this is going to be 20.0 grams of O2 divided by 100.0 grams of solution times now 1,000 to make it a parts per thousand. So 20 divided by 100 times 1,000 is 200 parts per thousand. Similarly, parts per million, we know the same mass of the solute and mass of the solution. So this is going to be 20.0 grams of O2 over 100.0 grams of solution times now 10 to the 6th to get parts per million. and that gives us 2.00 times 10 to the fifth parts per million. Really, my significant figures over here should have a decimal point there so that we keep the correct number of significant figures in the parts per thousand. So 200 point parts per thousand and 2.00 times 10 to the fifth parts per million. I hope you've enjoyed this video, and you should practice these problems on your own using the book or uh, any worksheets that are available. And I look forward to seeing you in the next video.